Okay. I'm gonna try to give you a picture how everything fits together. Coulomb's law through RLC circuits. Okay, we'll see how that works. But what's Coulomb's law tell you? Tells you how to get the force between two charges if you know their positions, right? So we have Coulomb's law. Um, two charges and positions. That makes sense? My notation. You know what the equations are. Okay, so there's Coulomb's law. An immediate consequence. You got, oh, that's about first mistake. Okay, I got a notation. Difficulty here. I want to use P and Q for 2 points, and I can't do that because Q has a connotation of charge. So I'm going to say we've got a Q1, P1, and a P2. We get the electric field. This is a force, and of course, it's a vector. Electric field is a vector in the direction of the force that would be exerted at a given point on a charge that you happen to put there. So, again, simple formula here. Got a bunch of charges and positions. And you have P prime. Yeah, something. E of P2 means the electric charge or the electric field at point P2. Okay. Got a bunch of charges in a bunch of positions, each had a given position at a point P prime. Electric field at P prime is the sum of the electric fields at the points. So I'm using I as a subscript here for a charge and a position. Each gives you an electric field at point P prime. and we add up all those electric fields. Now, we can illustrate that by P1, to P2, and some point P prime. Along this line, we get the force that we divide by whatever charge we're here. And this would be E1. And along this line, we get electric field might be toward the charge. If this charge is negative, this field would be toward the charge. If this charge is positive, then field would be there. So the fields could be anything, any direction, as long as it's along the line. Each field is going to be along the line that goes through the position of the charge and the point at which it acts. Now we do this little parallelogram. And see that the resultant field at P prime is E1 plus E2. And I represent that as a sum of EI. Now, I could have done this for a couple million charges, but I don't have time to write them out. You understand, if there are a bunch of charges along here, each charge will produce an electric field at each point of space. We're just selecting one random point, P prime. And the electric field is just the sum of all the electric fields. Okay. And then using notation a little bit, would actually generally be a triple integral of charge density at point P times the vector P prime minus P with respect to volume. That's a little bit of a loose definition, but you've seen these kinds of integrals. This is just pointing you toward those integrals that you should. Often Gauss's law. This is the integration. Okay, so implicit in everything I say here, I give you a collection of charges and ask you to find the electric field at a point. You should be able to do that. Now, I'm not going to give you a million charges. I'm going to try to keep it down to 10,000. Okay, seriously, I give you 2 or 3 charges. And maybe I asked you to find the field at point X, Y, Z. So a typical problem that might come up is just, let's say we've got three charges and a point. X, Y, Z. Say this is 4 microcoulombs. This is -3 microcoulombs, and this is 7 microcoulombs. Then what is your force diagram going to look like? Well, for your field diagram, your electric field here will be toward the point, because if I have a positive charge here, it's going to be attracted. I'm sorry, positive charge would be attracted toward this point. So we'd have maybe this much force. Really don't want that much force, but I'm going to make this into smaller charge. I'm going to make this into 2 microcoulombs. Because for 7 microcoulombs, I'm going to have a big long neck that just points a lot closer here than this one is. Okay, now, the 4 microcoulomb charge, that it is going to experience a field. It's a little bit bigger than this one, maybe, because maybe this one's a little further away, but it's a little bigger charge. So probably kind of a wash. These two would have about the same magnitude. Now, you can easily put the coordinates into the expressions, the electric field, and get those vectors. And then here, you might have, I'm drawing these arrows in the wrong place. I have a positive charge here, it's going to be attracted to this one, and it's going to be repelled from this one. And then if I've got the 2 microcoulomb charge here, again, it's going to be repelled from that, and that was kind of close, it might be. So your force diagram might look like this. Your net force might be polygon method. Add them up, find out. When I say force, your net electric field might look like this at this point. As far as the details of calculating, that's all very straightforward. You know how. Now, if I give you a line distribution of charge, continuous distribution, you should know how to do Gaussian surface, cylinder, and calculate the electric field. I'm not going to depict that. Depicted it, we've seen it in class. I've used plastic tubing along with a straight rod to demonstrate. Okay, that's an infinite plane charge. You ought to be able to derive that. It's a charge between two plates of a capacitor. You need to be able to do that. Okay. Charge on each capacitor. They're opposite charges, then they reinforce in between, cancel out. So refresh yourself from that. Now, potential. a potential change. Well, let's make sure I got this right. It's the integral E dot dr from A to B let's make sure I've got this right. Because talking about potential, which is a potential energy per unit charge. Okay. So potential is put the word unit in there just for space. Okay, I guess squeeze it in here. Potential energy per unit charge. Okay. Now, if I raise concrete block from here to here, you understand that its potential energy is increasing. It's at higher potential, gravitational potential here than it is here. Why is this? It's because gravity is doing negative work on it as I go here to here. So it's going to be equal and opposite to the work done by the conservative force, which is a definition I've been trying to drill into your head since September. Okay? With some success. That's what you come down to. Now, if I move from A to B, move a charge from here to here, positive charge from here to here. Okay? And the potential increases. And what's the direction of the electric field? Well, if the potential increases, that means I have to do positive work from here to here, right? Just like lifting that block, which means that the force has to be in this direction. Okay, so I think we better put a negative in this. If you ever get confused, go back to that block, think about the definition of potential energy, and then check what I'm telling you against what your book tells you. Sometimes I get it back. Okay. So potential change from here to here along any path is integral. It's equal to delta phi. I've got that sign wrong. Because if it's point A and this is point B, if the potential is higher here than it is here, that's clear. Because if I have a positive terminal here and a negative terminal here, try to move a positive charge from the negative to the positive terminal, it's going to repel. positive terminals here, the negative terminals here, the electric field is in this direction. So this has to come out 5B minus 5A. Well, the negative sign is here because the electric field is positive. That means the electric field is in the direction from A toward B. So you might want to sort that out, but that's correct. I've satisfied myself. But again, check me against it. Okay, the concept is simple. It's the work per unit of charge to go from here to there. If the electric field is in this direction, I've got to do positive work. Potential here should be lower. What's it? I'm getting confused. Think about it. What do you think? Okay, so I got a good response. Such as the action talking about the work field is doing, or you talk about the work you're doing. Okay. Well, definition is equal and opposite to the work done by the field. Okay. Well, if you move from here to here, the field, assuming this is positive, this is negative for the moment, then the field is in this direction, it's doing negative work. You're having to do positive work, so this is at higher potential. All right? And there's a direct analogy to lifting that concrete block. Okay. Potential clearly goes up, gravitational potential clearly goes up when the gravitational field is in the direction opposite to displacement. So that's something you just want to keep sorted out. Use electromagnetism to get into a lot of situations where you just use a formula and you all of a sudden lose track. Should that be a positive sign or a negative sign? Go back to the definition we've been using both semesters. Okay. Not MGH. But MGH in vicinity of the surface of the earth happens to be a consequence of the definition. Okay. So anyhow, so we've got this. Units. Well, potential energies in joules, charge is in coulombs. It's got to be potential energy per unit of charge is joules per coulomb equals sort of by definition volts. 9 volts. It's the unit of change in potential. Okay, now E integral V dot dr is path independent. Since the electric field is conservative, meaning that there exists a potential function phi such that E and by the fundamental theorem of finite, if you wish, okay, what's the integral of a conservative field from A to B? It's 5B minus 5A. Okay. It is right. You work it out. Okay. Makes sense? You want to make sense of all that, so you know what electric fields are. Yeah, the uniform conducting cylinder of length L and radius A. Let's call this point A. Point B. Delta phi is 5B minus 5A. Electric field is uniform. And we can write that as delta V over L since phi, the electric potential, is identified with volt. Okay. Now, the other thing we do is, you know, that we have magnetic potentials too. Put little e's from these phi's. It applies the same force on each unit of charge, which applies an electron drift. Constant velocity usually measured in millimeters and at most centimeters per second because there are a lot of electrons. Now you have to know how to put all that into the conduction model. We developed a conduction model where we did that in some detail. In the introductory problems, that's due 80% of it in sufficient detail. But they don't, I don't think the transition problems or introductory problem sets, whatever you want to call them, I don't think they address current density, do they? Maybe they do, maybe they don't. Okay. Well, if they do, they just say, well, the current density is the amount of current you got in this cylinder divided by cross-sectional area. Well, density is actually more fundamental than that. Okay. So this implies constant Okay, it means at any point you take a tiny bit of area in the direction of your vector J and multiply the magnitude of J by that area. That tells you how much current's flowing through there. Okay. I'll say J is I over dA, where dA is a small area increment. And I can't divide a vector by a vector. So that's an improper constructed. I'll say it this way. It's I dot M over dA, where dA is a small area increment normal to dA. It's not very distinct. Now, in the case of a uniform cylinder, which is a model for a wire or any conductor of any nice uniform. Okay, I'm leaving that term a little bit back. I'm going to get into details of definition. It means that the cross section typically be just a cross section perpendicular to the axis of the wire with the current density in the direction of the wire. Okay. So that I dot M, well, your normal to the area is going to be same direction as the current. Okay. If you happen to slice it with a plane, it's not perpendicular to the axis. Well, then the normal vector is going to be off by a little bit. You're going to have a little bit more area. So your I dot N will be a little smaller, but your area is going to be a little bigger. And it'll balance out. Okay. So remember that your current density J is a local property. It's at a point. In this case, it's going to be the same at every point. So you can just then multiply the current density by the cross-sectional area perpendicular to the axis. Okay? If you have another situation where you have like a narrowing wire, okay, well, your electric field's gonna change. It's gonna kind of follow the contours. You have to deal with that situation. Okay. So this embodies the essence of induction. Now, there are details, you know, to take your electron density and your cross-sectional areas, all that. Okay. But those details, I think, are well covered by the transition problems. There shouldn't be much question on them. You want to be sure you review these things. Okay. So what happens? Doctor here. If I find my way out of the maze, those things. Okay. Understand what we're saying now? We're gonna have current flowing. Have potential here. I'm going to use B. I keep wanting to put the A and the B subscripts. Bad impulse. I always have to go back and correct it. Let's assume that this segment of wire is short and this one is short, and they're good conductors and so forth. But these maybe are a couple pieces of nitrile with different diameters and whatever. Okay. So think good conducting copper here and nichrome here and here. Makes sense? Okay. What happens? Well, you presumably you have some current. Have a current I here, and you're going to have the same current coming out here because there's no place for charge to accumulate. So total current through here and here equals the current going in, and that equals the current coming out. It's one of Kirchhoff's laws. Very simple reason for it. current can't accumulate at a branch point, then what goes in must come out. Now, the reason I talk about this, you're gonna get more current if you switch, insert a switch here, and open the switch so that you no longer have continuous NyQuil. You're going to get more current if you open that switch or close that switch. Let's talk about that for a second, because it's something that I think, well, might be a point of confusion. There's several very fundamental points here that I'm not sure everybody's clear on. Okay. First question, what's the potential? Let's say the nichrome starts here and ends here, and everything else is copper, right? Well, this is nichrome, but everything from here to here and everything from here to here is copper. Now, it takes very little potential difference to run current through copper. Okay, how do you know that? If you're cranking the generator and you got some nice thick copper wire between the leads, you're going to have to exert quite a bit of force, meaning you're pushing quite a bit of current, right? Again, your cranking speed determines the rate at which that magnet rotates within a coil, or the coil rotates within a magnet. Okay? And that's rate of change of flux gives you the voltage, right? So the faster you crank, the greater the flux. And if you double your cranking speed, I said the greater the flux, greater the rate of flux change. The faster you crank, the more quickly flux changes. Some of you like to use the word Lenz as well. Just negative d phi dt equals your potential, your EMF. Okay. So again, when you crank and you feel a lot of mechanical resistance, it's because you're having to do a lot of work, which means that you're producing a lot of current through that voltage. Okay. If you replace that copper wire by good length of nichrome wire, it's very easy. Okay. I mean, you got a certain mechanical resistance in the apparatus itself. You're doing practically nothing to get the current through that nichrome wire because too much current. Okay. Okay. Now, your conclusion is it takes a lot of voltage to move a current through nichrome. If you want to feel as much mechanical resistance, you're going to have to crank a lot faster. And if you want to experience as much mechanical resistance cranking through a length of nichrome as you do cranking through the length of copper. Nichrome's about 100 times as resistant as copper. Okay, which means it has about 1/100th the conductivity. So my point is that you conduct current through the copper with very little voltage. There's very little voltage change from here to here or here. Okay, makes sense? Most of the voltage change is going to be in the nichrome. Okay, where's the voltage higher? Here or here? Assuming you neglect the voltage change to get through the copper, this is still copper. There's going to be no difference between here and here. there'd be a tiny difference. Okay, but if this is a short, fat piece of copper, it's not going to be much. It's going to be pretty well negligible unless you're going down to the microvolt. Okay, and the potential here is going to be the same. Okay, so given that, if you know the conductivity of nichrome, what's the current density going to be in here? And I could add this. Current density is conductivity times the potential gradient. Okay. Now we've got a potential gradient here. It's just going to be, well, what is the potential? There's a symbol on the board, gives you the potential. Well, there it is. There's very little change in potential between here and here because it's all thick copper. Okay, so V being here, also here. Let's be explicit. Got copper here, copper here. Nichrome from here to here, nichrome from here to here. The voltage VB here and voltage VA here. Make sense? Okay. If I open the switch, is it making any difference in the potential? The potential. Okay, the potential is VB minus VA, whether this switch is open or not. So we have an imaginary switch somewhere in this piece of copper. If that switch is open, potential difference on the lower path. It's the same whether this switch is open or closed. Okay. So the current density, which we can then multiply by the cross-sectional area of that chunk of nichrome. Same in either case. The total current is what? Pick greater, less than, same. Somebody said greater. I think somebody said less. Well, now, this current is going to change. You close that switch, is it? So it can't be less. Okay. If you close that switch, you're going to get a current up here. Close the switch, connected. Yeah, you're going to get a current up here. So your total current has to be greater. Right? So the conductance of this combination is greater if the switch is closed. You get more current for the same potential difference. Okay. So what would you say about resistance? Greater, less than, or the same. If resistance of lower branch. Tell me. Okay. Here. And I got less than, I guess. So we're kind of switching. At least you get turned around on this. If you want to be sure, you can reason this out. Okay. When you have higher resistance, that means you have lower current for the given voltage. Okay. Higher resistance, same voltage, lower current. Got the same voltage in every case we've done here. Okay. Now, when the switch is open, you say the resistance up here is infinite. Conductance is zero. Resistance, conductance are reciprocal quantities. Okay. So you have infinite resistance up here. You have whatever resistance this gives you, right? Okay. Or you have zero conductance and you have whatever this conductance is. Okay. Yeah, yeah, very good. Yeah, sorry for the mistakes.
No, we got things.
I was wrapping up the 162, and that was my focus. Then I mislabeled one. Anyhow, hope that didn't cause you.
No, they're good. They're all ready to go.
Thanks, Will. the world a little nuts right now. Okay. Spent last weekend on a big project. Sent out beautiful files and well good. Then a couple of ancillary files I sent out, just screwed them all up. Fortunately, they were sent out in time that we could get it straight. Okay, anyhow, focus on the big thing and overlooks the little thing. Be sure you don't do that. Okay. You can't control. It's human nature. And that's no excuse of mine. Okay, so anyhow, you got the resistance of combination. Well, okay, again, you go from infinite resistance up there and some resistance down here to lower resistance up there and same resistance down there. Okay. So total resistance. Well, it's still, how do you figure out what the total resistance is? You got a rule for parallel combinations. That's usually where people start without talking about why the rule is. Okay. And do exactly the opposite. Okay, well, again, you got more current. Okay. If the switch is closed. If you got more current, that means you had greater conductivity, means you had less resistance, right? So when, as at least one of you did, I don't remember which, I know somebody did, you take a parallel combination and add the resistances, you mess up. Okay. You should know you're going to get more current through a parallel combination because you have two alternate paths with the same potential difference. Okay. So now I'm taking up more time than I intend on this, which is a fairly minor part of things, but I'm addressing a misconception and addressing the conceptual picture you need of conduction in order to make sense of these very simple formulas. Which one gives you greater resistance? This one gives you the greater resistance because this one is the same as R equals R1, R2 with R1 plus F. This is greater. And you put that up. Or you just put a couple of numbers in, see. Okay. Or you can just say that, well, if you didn't have R2, then 1 over R would be the same as 1 over R1, so R would be the same as R1. Now, if you got R2, that makes 1 over R bigger, which means R must be smaller. So many ways to think about that. So don't make those kind of mistakes and expect that I might well ask a probing question about why these formulas are what they are, because it's all answered in the transition problem. So you might want to just look at the simple explanation I give you there. Okay. Pretty sure I give you a pretty good explanation. You can also look it up in your book. And we just spent way too much time doing. See, okay, well, anyhow. Okay, now capacitors. Um, That is not- A capacitor allows charges to be separated. So if you apply a voltage with a low resistance, with a apply a voltage to a conductor attached to the capacitor, the capacitor is uncharged, it'll separate charge until the charge on the capacitor is great enough that the voltage on the capacitor is equal and opposite to the voltage source. Okay. Capacitance is the ratio of the amount of charge you can separate to the voltage required to separate it. Parallel plate capacitor so, lost track of which. Okay, so here you've got the two plates. One of them is positively charged. That would be the one on the left because the field is away from the plate. The other is negatively charged because all the red arrows are pointing toward it. Okay. And also maybe we're just looking at a small section of the capacitor. Maybe we're not near the edges, in which case you would have no edge effect or negligible edge effect, so that all the electric fields are uniform and perpendicular to the plates. Uniform throughout space, as long as you don't get too far out in space that you're close to the edges. Okay, meaning that this field, and this field are going to be the same because the edge is 6 miles high and the opposite edge is 6 miles deep and all that. Okay, so these vectors all have the same length. It's just because it's an application of Gauss's law to a plane, and you should clearly understand that. Okay. Then all the red arrows point toward the plate on the right, meaning that plate must be the one that has a net negative charge. And these are, again, uniform through space. The charges are on the plates are equal and opposite. Charge densities are equal and opposite, so that these vectors all have the same magnitude. Between the plates of the capacitor, they reinforce. So you have a big field inside the capacitor. And each field is just the field that you get using Gauss's law. Okay. 4 pi KQ is the total flux through any surface. And you should know, of course, if you use surfaces that you can look like this. So you get 2 pi KQ out of this and 2 pi KQ out of this end and none on the parallel sides. And then the same for the other one, giving you a total charge of 4 pi KQ. Okay, K sigma, I'm sorry. 4 pi K sigma, or sigma over epsilon. Okay. And I'm not going to explain what sigma is, actually very familiar to you now. It is, I mean, I'll say it's charge density, but I'm charged per unit area. So take the total charge, divide by the total area of the plates. You should totally understand this. And then by extension, cylindrical or spherical capacitors. Usually put the C first. The potential difference is Q over V. V is Q over C. One half Q squared over C. That's the energy in the capacitor. If you divide that energy by the total volume between plates, you get the energy per unit volume. So you divide this by the volume, you get the energy density of this electric field. The area between the plates and volume. That smeared outward there at volume is energy. Density. The field 4 pi K sigma. Again, review the text. Verify that I did it right. check out the units. Okay. Also, as we've seen, well, got a switch here. Source, capacitance. And you've got some resistance. You get a current pi of t. So dq dt equals pi of t. Equals whatever your EMF is, minus Q over C times R. There's a differential equation. You can solve for Q of T. But imply that Q is some Q max times e to the negative T over RC. And you see that in the text. Okay. So you can look through the details or just use your knowledge of differential equations. Just multiply both sides by R. And then multiply what you left by C, and you're going to have RC over here. If this is constant, well, you just go from there. Okay. So I'll go through the details because they're straightforward. We've been through. So the other thing about capacitors, we've recently seen this, a reactance, okay, of a capacitor. It acts like a resistance. So you divide your source voltage by this. Get your effective current. And we'll pick up on this next time. Next time, what we want to talk about inductors and back EMF and all that stuff we've done more recently. And then, of course, we can analyze this circuit. There is a sinusoidal EMF. Still have the same equation, but this is going to become the sine function or cosine function, sine of omega t, cosine. Okay.